Welcome everyone to today's NOBIC Micro Talks. My name is Yong Hwee. I'm the Facility Manager of the Advanced Biofilm Imaging Facility in SCELSE. Today's talk will located more for users who might be interested in using our scanning electron microscope in SCELSE. So the title of my talk is Variable Pressure SEM, Scanning Electron Microscopy of Biological Samples without any preparation. Here, without any preparation means there is almost no sample preparation or sample treatment that is needed for the imaging of the SEM. The outline of the talk is, first I will introduce the SEM, followed by the variable pressure SEM. I will then conclude the talk by showing some of the images that we have taken from our very compact Hitachi SEM in our facility. The reason why we use electron microscope is mainly because we want to be able to resolve very small structures, for example, small proteins or small molecules. But of course, that is usually restricted to the high resolution TEM. So in electron microscopes, there are two types: the TEM, transmission electron microscope, as well as the scanning electron microscope, which I will cover for most of the talk today. So the main difference between the SEM and TEM, I'm going to highlight here. Let me bring out my, okay. So for TEM, it's mainly used to look at 2D projection, simply because you need to slice your sample very thinly over here, right? And compared to the SEM, usually you're using it to image 3D surface of your sample, right? And the magnification for TEM is obviously very much larger than the SEM, as well as the resolution, right? So TEM is usually used for high resolution imaging, whereas for SEM is typically used to look at the surfaces of your sample or specimen. The signals that can be generated when you illuminate or you shoot your sample with electron beams are as follows. So for TEM, you are looking at you're detecting the transmitted electrons. But for SEM, in general, you are collecting the secondary electrons as well as the backscattered electrons. There are sometimes some cases where you actually detect the X-rays to use for elemental analysis, but this is outside the scope of today's talk. So we will focus only on the SE as well as the BSE signal. So for electron, secondary electrons, the generation of secondary electrons is a result of inelastic scattering, which means that your incident electron hits the free electrons in the specimen, and the energy is then being transferred to that electron, and that electron gets propelled out of your sample. That's called the secondary electron. And that's mainly originate from the surface or a very small region of the specimen. So this has a higher resolution compared to backscattered electrons, which I will talk about in the next slide. So the intensity of the secondary electron, it depends on the angle of the incident electrons onto the specimen. Therefore, you are able to look at the topographic information or the surface roughness of your specimen, as shown here in this image. For backscattered electrons, BSC, it originates from a broad or broader regions of the specimen, as you can see here. It's a result of collision of incident electrons with atoms in your specimens that changes the trajectory of your electrons, and that's why it's called reflected electrons. And larger atoms, as you can see here, aluminium and copper, are a much stronger scatterer of electrons compared to light atoms. So for example, copper is more denser than aluminium. So the electrons tends to backscatter more in copper. So that generates a much higher intensity compared to aluminium. Of course, the incident angle of the electron beams also affect or gives you information about the topographical details, but that is much less compared to the secondary electrons. And from this slide, the setup of the backscatter electron as well as the secondary electron detector is as follows. So the BSE detector is usually on top of the specimen, and the secondary electron is on the side. Right? They detect either the low energy SE or the high energy BSE. So if you look at image A here, which is an image of a BS or BSD from a BSD detector, it contains very little topographical information, right? Compared to the secondary electron image here in C, right, where you can see all these different contours on your specimen. There's a technique called topography BSD, or well, that's mainly done by shutting down part of the BSE detector. So if you look at the BSE detector, it has 4 quadrants here. So if you just turn off 2 of these, right, and you detect the electron by 2 of these detectors, what you are selecting is backscattered electrons that comes from a certain angle. So that gives you some topographical information, but as you can see, it's not as good as the secondary electron detector. In a conventional SEM, you have to operate at high vacuum. This is to reduce the collision of electrons and air molecules. The purpose, the reason is quite obvious. You want to prevent the incident electrons. You want to prevent the incident. You want the incident electrons to reach the specimen, as well as for the generated electrons to reach the detector. Because you operate at high vacuum, your specimen must be thoroughly dried, right? Because the evaporation of water in high vacuum, especially in biological sample, can lead to poor signal and massive deformation of the specimen. This is why usually in conventional SEM workflow, you will have steps that you need to fix your sample. This is followed by dehydration. So this step will keep your sample structure intact. And when you remove water by a series of increment of ethanol or sometimes acetone, you actually remove most of the water content from your specimen. Right? And after that, you need to remove the ethanol by either air drying or using chemical drying agents. There's a method called critical point drying. This will also remove the ethanol content from your specimen. And the reason why you need critical point drying is for some samples, if you look at this water free, right, the air dry sample, you actually can see the specimen actually gets a bit deformed. The reason is because when you change from liquid phase to gaseous phase, for example, the ethanol becomes when you air dry, it becomes a gas. There's a change in surface tension, and that surface tension generates a force, and that might deform your sample, which is why you use critical point CO2. So CO2, liquid CO2 at critical point is actually is both a gas as well as a liquid. So when CO2 exchange with your ethanol, we replace your ethanol and it gets evaporated, there is no change in surface tension. That's the reason for using CPD. And in addition to remove removal of water, the specimen has to be conductive to prevent a phenomenon known as charge-up. Charge-up is a phenomenon where the negative charge of the incident electron beam accumulates on the surface of a non-conductive specimen, leading to imaging issue. As you can see here, all these shadows, these lines, is because of charging. And to reduce charging or to remove charging, you have to coat your specimen with a thin layer of metal. Right? So after all this procedure, you have to coat metal, either gold or platinum, on your sample in order for it to be conductive and to be able to be imaged under the SEM. Now, as you can see, the procedure here is pretty long. It is required because of the high vacuum as well as to make your sample conductive. However, there's a technique called variable pressure SEM, VP SEM. It operates at low vacuum. Right? The reason the reason for this is to image a non-conductive specimen in a non-destructive way. So at low vacuum, it suppresses the vaporization of moisture. So removal of moisture in the specimen is not required. Right? And the charge build-up or the charge-up phenomenon is prevented by the ionization of the residue gas in the chamber, which means that during the collision of the electron beam with the gas, it generates positive ions. That positive ions neutralize the negative charge accumulated on the specimen. Therefore, no metal coating is required. However, a small caveat is the secondary electron tends to lose its energy due to the collision with the residual gas. Therefore, the secondary detector is not able to detect secondary electrons, and typically a BSE detector is required in VP SEM. The result of this, because you are not detecting secondary electrons, which gives you a higher resolution, you are using a BSE, you don't have any coating, because the metal coating in a conventional SEM does give you additional signal, and because there's no coating, right, overall VP SEM tends to produce a lower resolution. This is for the sacrifice of all these sample preparation. However, contrast can be improved by heavy metal staining. For example, osmium oxide can be used to stain lipids. So you increase contrast for lipids. So now, basically for VP SEM, you don't really need to do any of this, right? Sometimes you might do some fixation in the event that you think even under low vacuum or you have a very delicate sample, you might have some deformation, but otherwise you don't have to do all these steps. Because you don't have to do all these steps, you are actually imaging your sample in a very native state. And I'm going to give you some examples. Right? In this paper, the author actually uses 3 techniques to look at the biofilm, especially the EPS on the biofilm. Right? So using conventional SEM as well as conventional SEM with a stain, this is rubidium red. It stains for the sugar groups in the EPS. If you look at both of these, right, the resolution is very high, but I don't see any major differences between these two. But when you put your sample under VP SEM, which is no treatment at all, no dehydration, you can see very drastic differences between the two images. Especially you see a very thin layer of film covering the biofilm. This is supposedly the EPS. So this technique, VP SEM, is basically non-destructive imaging compared to the conventional SEM. Before I go to the last part where I show you some images taken from our SEM, I will need to cover some of some similar types of detectors as well as SEM. Sometimes you might encounter ultra variable pressure detector, which can be installed in our SEM. Right? It's an optional add-on for SCELSE SEM. What this detector does is it actually can detect secondary electron under low vacuum. Right? So this is one option that can improve the resolution of VP SEM. There are other SEM available out there in the market. One such SEM is called environmental SEM. This is especially for very wet or hydrated samples, for example, sponge or some environmental samples that you take from I don't know, rivers or lakes or something that is really, really wet. It is coupled with a gaseous secondary electron detector, right, to operate at a much lower vacuum compared to VP SEM. There's also cryo SEM, right? You can use this for hydrated sample as well. Basically, you freeze your sample and couple it with a cold stage. That prevents the sample from drying. So now I'm going to show you some images that are taken from our SEM in SCELSE under using the VP SEM mode. Over here, you can see S epidermis biofilm image here. How this is done is basically I transferred the colony from an agar plate directly onto a membrane and basically just put it under the SEM. There is no additional treatment in between this transfer process. So what you see right here is basically the membrane. You see this, I don't know, fiber-like stuff. This is the membrane which I put the colony on, and the rest of what you see over this side and this side, these are the bacteria. As you can see, the bacteria are quite nicely packed, as shown supposedly in your single cell, single colony. This is another view of the colony. You can see the massive 3D structure here, and this is a membrane. Right? However, if you go to higher magnification, for example here, so what you see here is about 50 microns across here. Right? This is 50 microns. And you have about 1,000 times magnification. Compare with this, which is only about 20 microns, and you have about 2,500 magnification, the quality dramatically reduces. So basically, VP SEM, you can't use it, at least currently in SCELSE's facility, you can't use it to image single cell detail. Right? So if you want to look at single cell, it's really not possible because the resolution gets really bad. Right? In contrast, if you just do the conventional SEM where you dry and you coat it with metal, you can see even at 7,000 magnification and with a scale of 5 microns, the image is very, very clear. So this is the difference between the VP SEM as well as compared to the conventional SEM. So these are some other samples. So moving away from single cell, we look at, for example, the hair sample. So this is a hair sample donated by RADEC. And basically, there is no treatment. You just take the hair, put it under the VP SEM, and immediately you can image the details on the hair. Right? Over here on the right side, this is some flower which I picked from the walkway, and I put that flower under the VP SEM, and you can see all this stuff. I have no idea what these are. Most likely they are the pollens on the flower, right? And in addition, there are users that has used our VPSEM, and they have imaged a variety of samples. And unfortunately, I can't show you the images because those are not taken by me. So some groups have imaged flowers, parts of plants, insects like ants, and I have seen users imaging bacterial colony, right? So it's just like the S epidemias images, which I showed you a couple of slides earlier. And lastly, would like to end with some images from a sample which Radek took from the SCELSE pantry. So basically, he plucked off these leaves here, right? So if you actually note, there's some whitish stuff on top of the leaf. So when you put it under the VPSEM, you can quite clearly see I'm not a biologist, probably these are individual cells on the leaves. You can also see the stomata here, the openings, right, quite clearly. And when we move our specimens towards the whitish part, the coating on the leaves, you start to see all these fibers, right? So we are at very low magnification here. Okay. But still, this is good enough for us to see all these fibers. And if you actually know what those whitish stuff on the leaves are, they are actually measly bugs, right? These bugs, as you can see here, they secrete a kind of powdery wax substance as a protective coating, right? So using this technique, you are able to actually image insects or some pretty large specimens. Right? So to conclude, the VPSEM offers the imaging of specimen without the need of any conventional treatment. Right? All these images that I've shown you did not undergo any treatment. You just take the sample from either the agar plate or from the leaves. You put it directly under the SEM. Right? So it's suitable for non-destructive imaging. However, the disadvantage is poor resolution. As you can see here, even under 2500 magnification, the resolution is pretty poor. Right? So it has its own use. So if you have samples that do not require very high resolution imaging, you could consider using the VPSEM in our facility. Right? And lastly, if you wish to use the VPSEM, please contact either the NOBIC or you can just email me directly. Right? And lastly, thank you for your attention. And if you have any questions, I'm happy to answer them. So there's a question. Let's see. Can you play with the EV for imaging? Yes. So the electron, let me try. Yeah. Yes, you can play with the EV. You can change it from, I think, 2 to maybe, can't remember what's the limit, 20 or 50. I use 10 here because it seems to work very nicely with the backscattered electrons. But if you actually use the secondary electron, that's the image. Yeah, if you use the secondary electron method, right, you usually tends to use a smaller EV. Yes, so basically, yes, you can actually change the electron, the energy of the electron.
Hi, Yong Hwee. This is Harris. Thank you so much for the very nice presentation. I have a question. Yep. Let's say that if you have tissue sample that has been already PFA fixed, yep. Would that work?
It should work.
It should work.
Yeah, because the PFA doesn't really affect any part of the sample other than trying to keep it intact.
And then how is the, because I mean, you know, like in regular microscopy, we section the tissue and then we have to place it directly on the microscopy slide. In this case, if we have like a small tissue section, where can we place it? Like, is it a specific slide that we place the tissue section? How does it work exactly with that?
Because the mounting on SEM is quite small. We only have about 2.5 centimeter mount here, right? But you could actually cut the slides. If you are able to cut the slides into a smaller, or you can buy slides that are quite small, you can basically just place the whole glass on top of the mount. And that should work.
Okay, if it's, for example, like a cover slip, it would still work, right?
Yeah, yes.
Okay. Yeah. Okay, I see. And then a last question. You said that the sample shouldn't be wet.
Yep.
What do you mean? I mean, for example, let's a tissue sample would be kind of like, you know, wet. Do we have to dry it somehow, or like not partly dry it?
When I say wet, I don't mean like the tissue sample wet, but wet meaning like it's not in liquid media,
right?
Or it's not like for example agar or agarose. They have very high water content. Those actually will shrink even in the low vacuum. We have actually a user who actually cut out a piece of agar and placed it under, and I think after half an hour the agar starts to crack.
Right.
So those are considered wet or hydrated samples. But in terms of cells or tissue, if they are already kind of air dry or already PFA fixed and there's not much moisture content, I think that shouldn't matter that much.
Okay. Thank you very much.
See. Yeah, Isaac has another question. By the way, I'm not a prof. But anyway, I would like to try making a composite image of specimens using BPSEM. Do you have any tips? Well, it depends on what sample you are imaging, but basically, I think the trickiest part of BPSEM is trying to mount your sample onto this small stuff. For example, we have a professor from SES. He's imaging a flower. So the flower, he wants to image the opening of the central part of the flower. So as you can imagine, the flower don't just lie. You can't actually put the flower here and straighten the flower so that the top of the flower faces the detector. So you have to think of how to stick the flower such that the part that you want to image actually faces the detector. So I think that's probably the tricky part. Otherwise, it really depends on the sample. As long as the sample is not very wet, you can basically just stick it under the electron microscope and generate an image. There might be samples that we haven't imaged before and we probably need to optimize, for example, the energy of the electron or maybe the vacuum pressure settings. But by and large, I think if you wish to use it, you can just contact us and maybe describe a bit about the samples and we can take it from there. Yeah, thank you, Isaac. So I don't see any questions in the chat, and I guess there's no more questions. Right? If there's any questions, just feel free to email me or Radek, and we can try and answer them. Otherwise, thank you so much for coming to today's NOBIC Micro Talk, and I hope to see you guys in future talks as well. So thank you very much. Okay, and see you guys.